Okay, to pick up where we left off in part A, I was going over the scientific method. We pretty much finished that, but there is a figure in your textbook, which I kind of tried to reproduce here with my sort of lack of artistic talent. I'll let you look that over in the textbook version because this got kind of confusing. But anyway, it's sort of a graphic representation of the scientific method leading from observation at the very beginning through hypotheses to laws and theories. Another thing we have to get used to in chemistry or science in general, but particularly chemistry and physics, is we have to get used to looking at things on a different scale of sizes than we're normally accustomed to in everyday life. In chemistry, we have to deal with things like the size of individual atoms or molecules, which are really, 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 really small compared to anything that we deal with on a day-to-day basis. And on the other hand, we might have to deal with things like the number of atoms or molecules in a sample, which would be really, 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 really big compared to quantities that we're used to dealing with on a day-to-day basis. Okay, so the book classifies the size scales as macroscopic, microscopic, or symbolic. And macroscopic would be larger everyday scales. Things that would fall on a macroscopic scale would be things that are easy to observe, like density or flammability or solubility, things like that. The macroscopic scale, though, does extend upward into very large quantities that are not so easy to observe directly. Like I said a moment ago, the number of atoms in a sample. That's going to be an extremely large number. There's no way, even if you had all the time in the world, there's no way that you could count the individual atoms in a sample, even a small sample. First of all, the atoms are too small for you to see, even with the most powerful microscopes. And well, you'd have a hard time separating them from each other one by one, even if you tried to count, even if you could see them. And there'd be an enormous number of them. And also there's the micro scale, and that's stuff that's smaller than an everyday scale. And so that would be concepts like atoms and molecules, the bonding. When atoms are bonded together, that's what makes molecules. So the bonding would be the attraction or the connection between atoms. That's very small scale. This scale often has to be visualized through theory or through mathematical calculations because it's so small that we can't observe it directly. So if you wanted to know the number of atoms in a sample, well, there are ways that you can calculate that as long as you know what the sample is, what element or compound is it. And if you know how much it weighs, then you can actually calculate how many atoms or molecules are in it. But you can't actually count them individually. And then there's also the symbolic scale, which has to do with things like the symbols of the elements and the compounds. Each element in the periodic table, to get ahead of ourselves a little bit, the periodic table is where you store basic information about the chemical elements. The things that are listed in the periodic table, those are the chemical elements. And each element has a symbol, which is used as kind of a shorthand for the element by chemists. And that symbol consists of one or two letters. The first letter is always capitalized in any given element symbol. The second letter, if there is one, is not capitalized. And the symbols represent the names of the elements derived from the elements' names in English or sometimes Latin or Greek or German. And sometimes it's the name of the guy who discovered the element or the university he worked for, or so on. But anyway, we use the symbols for the elements when we put them together. When elements combine to form a compound, we write the formula for the compound as sort of a collection, basically, of the symbols of the elements that are in the compound. And so compounds can be symbolized by just using the symbols for the elements. And we can symbolize, symbolize chemical reactions by writing out the formulas for the reactants, the stuff you start with, in other words, and the products, the stuff you end up with. And that's all symbolic. Also, as part of these symbols for elements or compounds, we often use what are known as phase symbols. And that is an S in parentheses for solid, L for liquid, G for gas, and AQ, means dissolved in water. And that is a very commonly encountered way of dealing with things in general chemistry. So you're going to see the little AQ quite a bit. Okay. To move on, we can look at the classification of matter. There are a lot of different ways to classify matter, as we will see, believe me. First of all, just a reminder that matter is anything that physically exists, which means anything that has mass and volume. Even when the mass and volume are very small, so things like individual atoms or molecules, or even smaller things like electrons, they're very, very, very small, but they still have some mass and some volume, so they are matter. The main way that we classify matter is according to what's known as the phase or the state of matter, and that would be solid, liquid, and gas. So some of the scientifically relevant properties of those phases are what we'll go over now. Solids, and the book doesn't state all of these, but it's actually good for future reference. The characteristics of solids, liquids, and gases are almost entirely based on the strength of the attractions between the individual particles that make up the substance. Okay, so sometimes you'll have individual atoms or molecules that are very strongly attracted to one another, and that means they're hard to get apart and they're hard to shift around. And other times you'll have particles that are not attracted to each other at all, which means there's nothing to keep them together. So they fly apart and they go off in all different directions. And that's really what the properties of solids, liquids, and gases come down to. How strong are the attractions between the particles that make up the substance? And as to why the attractions might be strong or weak or somewhere in between, we'll get into that later. So don't worry about that right now. But anyway, for solids, you can probably guess, for solids, the attractions between the particles are relatively strong. And these are known as intermolecular attractions because they're attractions between molecules, but sometimes they're between atoms also. So if you have very strong attractions between the particles, what does that mean? Well, it means the particles are likely to be close together and more or less fixed in place. They don't like to move around relative to one another. So they're not easy to separate because they're strongly attracted to each other, kind of like two strong magnets. They can't move around or past each other. Moving around and past each other from one place to another is known as translational motion. You don't have that in solids. But they can vibrate in place. So even though the particles in a solid are strongly attracted to one another, they are actually vibrating in place. We don't notice this. I mean, it looks like the paper here, which is a solid, obviously, is sitting perfectly still. But in reality, on a very tiny scale that we can't see with our, well, we can't see at all, the atoms or molecules that make the paper up are actually vibrating in space, even though they're fixed next to each other. They can't move around and past one another, but they can vibrate in place. And that the rate of vibration depends on temperature. The higher the temperature, the faster the particles vibrate. And that's actually one reason that phase changes are related to temperature. If you heat something up enough, that vibration gets going so fast that the attraction between the molecules isn't able to keep them together anymore, and they break apart and start moving. And then you have a liquid. But we'll get the phase changes in more detail later. Anyway, when it comes right down to it, what solids are often described as anything that has definite shape and volume. So if you take something that's a solid, it has a definite shape. If the shape doesn't change, if you move it from one place to another, if you put it in a different kind of container, the shape of the solid remains the same, and it has a definite volume. So the size of it remains the same also, regardless of the conditions. So definite shape and definite volume, because the particles are strongly attracted to each other, and that's solids. For liquids, their intermolecular attractions are middling, kind of moderately strong. And so essentially liquids have some properties of solids and some properties of gases. They're sort of in between. So for liquids, because of the moderately strong intermolecular attractions, the particles are close to each other, but they're not fixed in place. They can move around and past each other with some difficulty, because in a liquid, the particles are close together. So in order to move around and past one another, they have to push other particles out of the way. So it's not something that happens really easily, but it can happen. And this is known as translational freedom or translational motion. So liquids do have that. And at the same time, the particles in the liquid are still vibrating in place. Or even if they're moving, they're still vibrating as they move. And that is still temperature dependent, like it is for solids. Liquids have a definite volume, but no definite shape. Or in other words, if you take a liquid and put it in a different container, it will adopt the shape of the container, but it will not expand to fit the container, and it cannot be compressed to fit into a smaller container. Okay, so liquids are not compressible. And neither are solids. And that, of course, is because the particles are already really close to each other. For gases, that is the other end of the range of intermolecular attractions. For gases, there's essentially no attraction between the particles. There's nothing holding the particles together. And so they're not close together. In fact, the particles in a gas are far apart relative to the size of the particles, and they're in constant motion from one place to another, as well as vibrating. So the translational motion, that is motion from one place to another in gases, occurs in random directions in straight lines at very high rates of speed until the particle hits something. Could be another particle, it could be the wall of a container, could be you. When the gas particle hits something, it bounces off and goes in a straight line in a different direction, again at a high rate of speed, until it hits something else, and so on and so on and so on. So if you were to map out the route of travel of a particular particle of gas, in a sample of gas, it would take the form of a bunch of little straight lines zigzagging all over the place in different directions. But all of those little line segments, they would all be straight lines. And it would happen very quickly because gas particles are moving very quickly. I think, sorry, at room temperature, the nitrogen and oxygen molecules that make up most of the air we breathe are zipping around at something like 1,000 miles an hour. Very, very high rate of speed. That's because there's a certain amount of heat energy. Heat energy is related to motion. It's related to the vibration of the particles, but it's also related to the speed with which the particles move if there's nothing holding them back, like in gases. And so even at room temperature, at very moderate temperatures, there's enough thermal energy to get these particles moving at a very, very high rate of speed, because the particles are really, really small and very light. The speed with which the gas particles move will depend both on the mass of the gas particle and also the temperature. The larger the mass, the slower they tend to move, and the smaller the mass, the faster they tend to go. And the higher the temperature, the faster they tend to go, and the lower the temperature, the more slowly they tend to go. And they're also vibrating the whole time. Gases, when it comes right down to it, are often said to have no definite shape or volume. Okay, so if you take a sample of gas and put it in a new container, it will adopt the shape of the container, but having no definite volume also means that it will expand to fill the container. And that's because, again, there's no attraction between the particles, so the particles are far apart, and they're in constant motion in every direction. And so if you put them in a new, bigger container, the fact that they're in constant motion means that those particles will start probing the outer limits of the new container almost immediately. And so they take the shape of, gases will take the shape of their container, and they also will take the size of the container. If you put them in a larger container, the gas will expand to fill the container. If you put a gas in a smaller container, the particles will come closer together, and that means that gases are compressible, unlike liquids and solids. And their gases, again, are compressible because the particles begin far apart from each other. And so it's easy to push them together. There is a limit. If you push them too close together, then they start repelling each other. And that doesn't usually happen, though, until they're sort of on the verge of condensing into a liquid. But yes, gases are compressible within broad limits. So yes, they take the shape of the container and they expand to fill it. The book includes a fourth state of matter, which is a plasma. This is general chemistry. We don't really need to know a lot about plasmas, but suffice to say that plasmas tend to exist in a situation where you have a superheated gas, like in a blowtorch or a bolt of lightning or stars, something like that. And as a result of that, some of the gas particles will ionize. And that, in other words, they have electrical charges. And because they have electrical charges, well, the ones with positive charges are attracted to the ones with negative charges, and they start sort of coalescing into something that's similar to a liquid. So plasmas essentially are very hot, and they have some properties of gases and some properties of liquids. Sorry. And the book also mentions that solids can, in some cases, behave almost like liquids if the particles of the solids are small enough on our scale of judging things. So like grains of sand can be poured out, from one container to another, almost like water. But the individual grains are still solid, and they still have the properties of solids. Okay, getting into characteristics of matter like mass. Here we'll go into a little more detail. Mass is a measurement of the quantity of matter in an object or a sample. Okay, it's not affected by gravity. And so mass is an inherent property of any given object or sample. So as long as you don't change the sample or the object will always have the same mass. This pen has a certain mass, and that will always be its mass unless I change it in some way. Like if I chop a piece off of it, then it'll have a smaller mass. But as long as I don't change it, it has the same mass, and it doesn't matter where I take it or what I do with it. As long as I don't break a piece off or something like that, it'll still have the same mass. The metric unit for mass is kilograms. And the English unit for mass is not pounds, but slugs. This brings in kind of an interesting contradiction in that we tend to use terms mass and weight interchangeably, but they're actually not the same thing. So in weight, we see weight is definitely related to mass, but it's not the same thing. Weight is actually a force. It's a downward force caused by gravity pulling downward on your mass, or on the mass of an object or sample of objects. The metric unit for weight is actually newtons. Newtons are the unit for force in the metric system, and weight is a force. So you would use newtons for weight in the metric system, but the English unit is pounds. So when we talk about weight, quote unquote, in the metric system, we usually describe it in kilograms, which is actually mass. Whereas in the English system, we quote it in pounds, which actually is weight. So if you're in the mood to maybe mess with the head of, if you have any Canadian friends and you sort of want to mess with their heads, ask them what their weight is, and they'll give you a number in kilograms, and you'll be able to say, aha, that's not your weight, that's your mass. Your weight should be in newtons. And then you can show them up for knowing more about the metric system than they do. Of course, knowing Canadians, they're polite enough that they'll probably give you their weight in pounds anyway, so that would screw things up. Weight changes with gravity because it's a force that's caused by gravity. So weight is directly proportional to gravity, assuming the mass doesn't change. And the way we write that mathematically is W and then the Greek letter alpha G. The Greek letter alpha is the letter that eventually developed into the English A, or the Roman A, actually, which we use today. And when it's printed, it often looks something more like this than the way I draw it. And let me try that again. Yeah, okay, when it's printed, it often looks something more like that. That's hard for me to do that, obviously, so I usually end up drawing it more like this, which looks kind of like a fish. But it's the same letter, and when it's printed, you know, with like in Microsoft Word, you can kind of see how that developed into our lowercase a. Anyway, mathematically, the Greek letter alpha means proportional to, which just means that, for instance, if you double gravity, you double the weight. So like if your weight is a certain amount here on Earth and you travel to the moon where gravity is 1/6 what it is here on Earth, your weight will be 1/6 what it is here on Earth. If gravity stays constant, then weight is proportional to, weight is proportional to mass. If gravity stays constant, then weight is proportional to mass. Sorry. The reason that we often use weight and mass interchangeably, even in science, we use those terms interchangeably very often, is because as long as gravity is not changing, as long as gravity doesn't change, then weight doesn't change. And so you can kind of use the two interchangeably. And here on Earth, the gravity of the Earth pulling downward on an object stays pretty much the same from one place to another. It does vary a little bit, but not significantly. And so that's why, as long as we stay here on Earth, we can use mass and weight more or less interchangeably. But in physics, where you're often talking about astronomy and things on other planets, then you have to be much more careful about distinguishing between the two. So remember, mass is not affected by gravity, but weight is affected by gravity. And as long as we're talking about matter and mass, we might as well mention the law of conservation of matter, or also known as the law of conservation of mass. What this says is that matter cannot be created or destroyed. It can just be changed in form, or it can be transferred. So what that means is that the total amount of matter in the universe is constant. And one exception to this is the idea of nuclear reactions. And just as an aside, in nuclear reactions, matter can be converted directly from matter into energy. And so the amount of material that comes out at the end of a nuclear reaction is slightly smaller than the amount that goes in. And it appears that mass has disappeared. What it's really happened is it's been transformed into energy. And that's what Einstein's equation E = mc² is about. E is the energy that comes out of a nuclear reaction, m is the mass that's converted into energy, and c squared is the speed of light squared. And when you take the mass that's converted into energy times the speed of light squared, you get the amount of energy that's produced. But anyway, in that case, matter is being changed in form, but it's not being created or destroyed. And what it means is when you're doing a chemical reaction, you have to end up with the same number of atoms of the same elements coming out as you originally had going in. And this is a law of science, so it's always true. There are no exceptions to it, even though there may appear to be exceptions, like nuclear reactions for one thing. Like I said, the energy or the matter is being changed in form, changed into energy, but it still exists, basically. In chemical reactions, we often do reactions that say involve gases, which can come from or escape to the atmosphere. If you were to take a nice, new, fresh, shiny, clean piece of steel and weigh it, and then put it outside for a few days and, until it starts to rust, you can then bring it back inside and weigh it again, and it'll weigh a little bit more than it did before. And you might think, oh, that extra mass just came out of nowhere because I didn't do anything to this. I didn't add anything to it. But what you're not accounting for is the fact that the iron reacted with oxygen from the air to form iron oxide, which is rust, and that's why it's heavier. So if you take the original mass as the mass of the piece of steel plus the mass of the oxygen from the air, then the mass before and the mass after would be the same. Okay, so and also, since you have to have the same number of the same atoms, or same number of atoms of the same elements coming out of a chemical reaction as you have going in, that also means that the mass that you have after the reaction has to be equal to the mass that you had before the reaction. And we'll use that quite a bit in the future. That, I think, is a good place to stop this segment of the lecture, and I'll start with pure substances when we come back.